So if you made it through the last video where we did our really challenging examples, you're probably a little bit worried about seeing the start of this video, thinking there's more to this section, and generally stuff gets harder as it goes on, so maybe you're worried that it's going to be even harder than the last section. I got good news. It's not. I threw this at the end because, I don't know, it's kind of supplementary information. It's not the main topic of this section. The main topic of this section is being able to apply these three different derivative rules that we learned. The power rule, what I refer to as the coefficient rule, and then the sum and difference rule. But really, if you're watching through all these videos, what you've learned is that often the challenge of using those rules is not applying the rules themselves, but being able to recognize the appropriate algebra that you need to do to get an expression in a form where you can use those different rules. Anyways, that's the main topic of this section. That's what I really want you to be good at. But now that we have the ability to figure out derivatives without having to do the really challenging stuff of evaluating limits of the difference quotient, we can apply that knowledge to a couple different cases. And so the purpose of this video is just to show you a couple of applications of what you've learned how to do. If I'm being perfectly honest, they're not super cool or anything, but it's useful applications for later on in the class, and this seems like a good time to teach them. So without further ado, it's easy to lose connection between what we're learning about derivatives and what the derivatives are really figuring out. So we first learned about derivatives talking about tangent lines. So here's a function. I guess we're calling this function f. And I have the equation of the function right here, x squared minus 4x plus 1. Suppose for some reason I'm interested in the tangent line to this function at this point right here, 3, negative 2. If you can hear my dog panting in the background, it's because I took him on that walk that I promised. We learned in previous videos how to sketch the tangent line, and we even talked about calculating the slope of the tangent line. But in this video, what I want to do is find the equation of the tangent line. I want to be able to completely define this line that you see pictured in green. And the way I'm going to define this line is, well, I'm going to give you its equation. It's a line, which means its equation is going to be in the form y equals mx plus b. And it's up to me to figure out the m and the b, the slope and the y-intercept that completely define this line. Well, because I drew it so pretty for you, you might be able to just look at it and tell what the slope is and be able to extrapolate to figure out what the y-intercept is. But what I want to do is all of that completely algebraically. Suppose you didn't have this graph, you were just told that the function is x squared minus 4x plus 1, and what you were supposed to do is find the equation of the tangent line to this function at the point where x equals 3. Because we have the graph, we know the y-coordinate of that point is negative 2, but pretend you don't have any of that stuff. This is all the information that you have down here in green. Could you solve this problem? Well, if the answer was no, I probably wouldn't be asking it. So maybe a better question is, how do you solve this problem? Well, again, our answer will be in the form y equals mx plus b. So we need to figure out m and b. Let's start by figuring out m. M is the slope of this line. To figure out the slope of this line, we need to know the derivative of this function. Good news, derivatives are a lot easier to find now. In fact, this is probably a one-step process for you at this point. You can probably look at this and tell that the answer is 2x minus 4. And while you're likely able to figure this out directly, I'd like you to be able to at least see all these different steps, understand why our rules allow us to figure out this derivative is 2x minus 4. Because again, a big challenge of calculus is overusing rules in situations they don't apply. And in the specific example, it's pretty obvious where the rules apply, but if you're not really keeping yourself honest there and really understanding the different steps, it'll cause trouble later on. Anyways, f prime of x equals 2x minus 4. This is a function, a machine, that tells me the slope of the tangent line to the function f of x at any value x. So if I want to know the slope of the tangent line to this function at x equals 3, in other words, the slope of the line pictured here, all I have to do is evaluate f prime of 3. F prime of 3, I copy this equation, changing all the x's into 3's. I get 2 times 3 minus 4, in other words 6 minus 4, in other words 2. The m in y equals mx plus b equals 2. That's awesome. If I could just figure out b, I'd know the equation of this line and I'd be done with the problem. Think back to the first thing we learned in our class when I spent some time focusing on linear equations and how to come up with slope-intercept form. I said one case in particular that'll be really useful is when you have the slope and one point on the line and you want to figure out the equation of the line. That's exactly the case we're in right now. We figured out the slope because we can calculate the derivative and plug in 3, and we have one point on the line. Technically, we have 1 point on the line if you look at the graph, and I told you to just consider the equation. So maybe you could argue that we're one step away from having 1 point on the line. But the idea is we want the line that's tangent to this graph at x equals 3, which means the line touches the graph at this point, which means that this point is not only on the graph, but it's also on the line. We need a point on the line to come up with this equation, but we can take advantage of the fact that the point is on the graph to find the y-coordinate of the point. If we evaluate f of 3, not f prime of 3, but f of 3, by copying this blueprint, changing all the x's into 3's, 3 squared minus 4 times 3 plus 1, we get 9 minus 12 plus 1. In other words, negative 2. We see that the y-coordinate of the point on the graph when the x-coordinate is 3 is negative 2. So from evaluating f prime of 3, we figured out that the slope is 2. From evaluating f of 3, we figured out that the y-coordinate on the graph of the point with an x-coordinate of 3 is negative 2. And because our line is tangent to the graph at that point, this point 3, negative 2 is on this line. So we have the slope and we have one point. Point slope form maybe? Y minus y1 equals m times x minus x1. Remember that from a couple of weeks ago? We have m, we have x1, we have y1. All we got to do is plug in. Y minus negative 2 is equal to 2 times x minus 3. This is an equation of the line, although typically when people say the equation of the line, they're thinking about the equation as given in slope-intercept form, not point-slope form. So it's not a bad idea to algebraically manipulate this so that it looks like this. I got y plus 4 equals 2x minus 6. I got y equals 2x minus 10. The line that's tangent to this red graph at this point 3, negative 2, in other words, the line shown in green, has an equation of 2x minus 10. Oh yeah, that looks reasonable. It looks like the slope is about 2 because the line goes up 2 units each time it goes right 1 unit. And it looks like the y-intercept would be somewhere way down here. Negative 10, yeah, that seems reasonable. I've got my answer. Using these rules to calculate derivatives easily allows us to figure out the equation of the tangent line to a graph at a given point. It feels like not enough to just show you one example and assume you're good with it. So here's a second example. See if you could figure out the equation of the tangent line to this function g when x equals negative 2. What would you do? Well, for the equation of the tangent line, we definitely need the slope. To figure out the slope, let's calculate the derivative, g prime of x. Using my derivative rules, maybe I'm at the point where I can just look at this and tell that it's 1/4 times 3, or 3/4, x to the second power, minus 1 plus 0. In other words, g prime of x is 3/4 x squared minus 1. So if I was interested in figuring out g prime of negative 2, all I'd have to do is change all the x's in this expression into negative 2's. Negative 2 squared is positive 4, and 3/4 times 4 is 3. So g prime of negative 2 is 3 minus 1, in other words, 2. The slope of the tangent line to this function at this point is positive 2. If I just knew one point on the line, I could figure out the equation of the tangent line. I can find one point on the line by taking advantage of the fact that this line is tangent to the graph at this point. So a point that's on the graph is also on the line. To figure out a point on the graph, all I got to do is figure out which y-coordinate corresponds with this x-coordinate of negative 2. That's just evaluating g of negative 2. It's really easy to get confused because you're calculating g prime of negative 2 and g of negative 2, and they're both going to give you numeric answers. But make sure you're keeping straight what these things mean so that you use those answers in the right spots. G of negative 2, the y-coordinate corresponding to x equals negative 2 of this graph is 1/4 times negative 2 cubed minus negative 2 plus 1. Negative 2 cubed is negative 8, and negative 8 times 1/4 is negative 2. When I'm subtracting negative 2, I'm really just adding 2. So I got negative 2 plus 1, which is just 1. You don't have to write this, but maybe parenthetically, we figured out that the slope of the line is 2, and the point negative 2, 1 is on the graph, and therefore also on the line. We got the slope, we got a point, we're good. Y minus y1 equals m times x minus x1, the point slope form of a line. So we got y minus 1 is equal to 2 times x minus negative 2. Simplified things a little bit, y minus 1 equals 2x plus 4, because when I'm subtracting a negative, I'm adding 2, and this 2 times this 2 gives me this 4. Now I add 1 to both sides to get y equals 2x plus 5. This is the equation in slope-intercept form of the line tangent to this graph at this point. Even without ever looking at the graph of this function, we were able to figure out the equation of a specific tangent line. However, I am able to figure out the graph of the function. This is what it looks like. Note that the point with an x-coordinate of -2 has a y-coordinate of +1, as we figured out over here. The tangent line would look something like this, and if we needed to figure out the equation of this line, well, I'm claiming it's 2x plus 5. Does that make sense? Yeah, it looks like this thing goes up 2 units each time it goes 1 unit to the right. And if we were to continue this line to figure out where it crosses the y-axis, looks like that would happen at about 5. I mentioned that this video is kind of supplementary stuff, sort of extra stuff that I wanted to tack on before ending this section. There's really 2 things. I could have made it 2 videos, but this last thing is so short that I think I'm just going to toss it in on this one. Another useful application is figuring out when a graph is flat. And I know right now that might not seem important at all, but it turns out figuring out when a graph is flat, loosely speaking, is super important. It's probably the single most important application of Calculus 1. So we have this graph, g of x equals 1/4 x cubed minus x plus 1. I might as well reuse it here. And just by looking at it, it looks like there's 2 points where the graph gets flat. Somewhere in here the graph is flat, and somewhere over here the graph is flat. If I were drawing tangent lines, my tangent line would be horizontal here, and it would be horizontal here. Say I wanted to know the x-coordinate where my graph gets flat, where the tangent line is horizontal. Well, one answer would be this value, whatever that is, a little bit more than 1. And one answer would be this value, whatever that is, a little bit less than -1. But what are the exact values? Turns out we can use calculus to figure that out. The important characteristics of these points is that their tangent lines would be horizontal. What is the slope of a horizontal line? Well, it goes up 0 units each time it goes 1 unit to the right, so its slope is 0 divided by 1, in other words, 0. Figuring out when the graph is flat is equivalent to solving g prime of x equals 0. And you could just memorize that this question kind of translates into this question, but if you can understand why, then it's a lot less memorization. G prime of x talks about the slope of the tangent line, and when the slope of the tangent line equals 0, that means that the graph is flat. So how do we figure out what x values lead to a horizontal tangent line? Well, we'd want to know what g prime of x was equal to. Finding g prime of x is really easy because we have these derivative rules. The derivative of 1/4 x cubed minus x plus 1, as we've seen above, is 3/4 x squared minus 1. I want to solve g prime of x equals 0, and I now know g prime of x. All I have to do is take 3/4 x squared minus 1, set it equal to 0, and solve for x. Solving this equation for x is easy. It doesn't involve any calculus at all. We'd add 1 to both sides of the equation to get 3/4 x squared equals 1. Since we want to eventually isolate the x, we're going to first isolate the x squared. So we'll multiply both sides of the equation by 4/3 to get x squared is equal to 4/3. If it helps, you can do that in 2 steps. Multiply both sides by 4, and then you get 3x squared equals 4. And then divide by 3, and you get x squared equals 4/3. Anyways, then you take the square root of both sides of the equation. Make sure that when you take the square root of both sides of the equation, you put in a plus or minus. I get x equals plus or minus the square root of 4/3. I don't know what the square root of 4/3 is. You can figure it out if you wanted to get a calculator. You get some decimal approximation. It's some number that's a little bit more than 1. So since my answer is plus or minus that expression, I get a positive answer that's a little bit more than 1 and a negative answer that's a little bit less than -1. I get exactly these 2 points right here, the 2 points where the slope of the tangent line to the graph is horizontal.